Okay, so in the last class we saw overview of few other techniques, and we also started with the experimental aspects of performing EAS. There are different type of equipment we saw. There are certain things one need to take into account when you do the experiments. You can use what's called Faraday cage. Faraday cage is basically a metal box in which you can keep the experimental setup. You have to use short cables if you want to avoid inductance at the high frequencies. Usually we will get information at the mid and low frequencies when we want to look for kinetics and mass transfer. High frequency information is usually for the double layer capacitance, and there are different types of sinusoidal waves one can use. One is called single sine or pure sine, another is called multi sine, which is basically addition of few sine waves together. Okay. So today what I want to discuss is to look at the electrochemical aspects. When you go to electrochemical cell, the current versus potential, that is not linear. Earlier we saw that current is related to potential in exponential fashion, at least for basic elementary reactions. For actual reactions, in many cases you will find that the elementary reactions can be as exponential, but still the net current may not be exponential. But by and large it will still be non-linear. So I want to show you what happens when you have non-linear current potential relationship. Next, few aspects of FFT and digital filters, because the experimental data that you get, it goes through some processing before you get it, and when you face any problem you should be aware of how this is processed, so you can decide whether it is because of the system, electrochemical system, or whether it is because of the way it is processed. And we will probably start with multi-sign and see what level we can go into, otherwise we will continue tomorrow. I think all of us are familiar with the linear system. When you have a relationship saying y equal to a plus bx, x can be a vector, y can be a vector, you give a sinusoidal input, call it as x, the y will be a sinusoidal output. With a constant offset, with a phase difference, that is okay, but it is going to be sinusoidal. When you have a nonlinear system, a sinusoidal input will give sinusoidal output plus harmonics. Harmonics means if the frequency of the input, if we say frequency is 0.1 hertz, the output will contain 0.2, 0.3, 0.4. So, integer multiples of the base frequency. That base frequency is also called fundamental. We will say the response at fundamental, response at the second harmonic, third harmonic, fourth harmonic, and so on. So, these are higher harmonics. So, an example, look at this equation, y equal to 5x square plus 3x plus 2, and let us substitute the sinusoidal wave as EAC0 sin omega t, that is what we normally use for potential sine wave. You get 5x square plus 3x plus 2, and you can expand it, you are going to get 5 EAC square sin square omega t, it is very straightforward. Next, sin square I can write it as cosine 2 omega, there is a relationship between sin square and cos 2 omega. So, I do not want sin square, sin cube, sin power 4, but I want to write it in. So, the first one would come in Taylor series expansion, the second meaning cosine or sine in n omega, 2 omega, 3 omega, they are in what is called Fourier series. So, if you write like this, you can rearrange it, you can get 1 by 2, 5 by 2 is 2.5 EAC square. So, the first part is the DC offset, first part here meaning this part is the DC offset, this is the response at fundamental, this is the response at second harmonic. So, instead of writing it as cosine, I can also write it as sin 2 omega with a pi by 2 phase. So, notice here that square term has given rise to a constant and 2 omega. Okay. If I have a cubic term power 3, that will give rise to sin cube will give rise to 3 omega and omega. So, on the right side sin cube, if I expand, I will get sin 3x and sin x. If I have sin power 4, I will get 4, 2 and 0, which is basically a constant. So, if I give in general sin power n, I will get n omega, n minus 2 and so on until it ends at omega for odd number of n, it ends at a constant for even number of n. So, when I get higher and higher nonlinear terms, correspondingly I will get higher and higher harmonics. Now, we know that for simple reactions at least, that the current and potential are related exponentially, which means when I write potential as DC plus AC, and I would write for a very simple reaction, F is the Faraday constant, K e power B e, B is a exponential factor, K is the pre-exponential, and we assume concentration of whatever species involved is a constant. So, that is absorbed into the K. So, I would normally have multiply by concentration of the reactant, but I can combine that with this if I say that C is a constant throughout the experiment. This case I will substitute for E, I will get E dC plus E AC. AC component is expanded as AC 0 sin omega t. At this level, DC potential may or may not be small, it may be 0, it may be 100 millivolts, 200 millivolts, 600 millivolts, maybe minus 600 millivolts with respect to the equilibrium potential. We are not making any assumption about the DC potential. At this stage, I would separate the DC and AC component and then expand the AC component in Taylor series. E power x, you can write it as 1 plus x square by 2 factorial, x cube by 3 factorial and so on. Now, if I assume that the product B and EAC 0 is a small number, then I can truncate this series after this term. I can say EAC 0 is very small, so the product B EAC 0 is also small, EAC 0 square is significantly smaller than EAC 0. So, if I say EAC 0 is 10 power minus 3 volts, that is 1 millivolt, it is going to be 10 power minus 6 for EAC 0 square. So, I can neglect those terms. With that assumption, we can make an approximation and say this is approximately equal to 1 plus. So, if I say that EAC 0 part amplitude of the sine wave is small, then I can truncate this and say I will get a linear response. System is non-linear, but my input is very small, small changes there. So, the output I can approximate it as a linear curve. So, if I draw it in a curve, this curve is non-linear. I can take this and approximate this area by a small straight line. I can approximate this area by a different straight line. I can't approximate this much area by a straight line, that will be a poor approximation. So, DC potential is not important for this approximation, the AC perturbation AC 0 amplitude has to be small. When that is small, we say yes, this can be linearized. When it is linearized, the analysis becomes lot simpler. That is the purpose of doing this. So, normally you would expect the current would come in the first order and with harmonics. First order is the fundamental and with harmonics. But if the perturbation is small, you can say that it is going to be linear system. It is going to respond like a linear system at that DC potential. Move to another DC potential, it is going to respond like a slightly different linear system. We are not saying throughout this potential, throughout this current range it is linear. We are saying around this, if you move a little bit, I can approximate this by a linear system. So, if it is a really linear system, you can do this perturbation in one level and then say throughout this range I can tell this is what it is going to be. But because it is non-linear in real life, but non-linear analysis is hard, therefore, we want to perform linear analysis, we have to conduct experiment at multiple locations and then say at multiple locations we are approximating by few linear segments, and this will help us understand or reconstruct this entire system behavior at various levels. Now, how small is small? People use 1 millivolt, 5 millivolts, 10 millivolt, 20 is probably stretching it. If you say 10 millivolts, nobody will question too much about that. If you say 1 millivolt, people will not question that it is linear or non-linear. It is definitely good enough to approximate as a linear system, but noise level will be high. Noise level in the system is random noise from outside. Okay, that is going to be independent of what is the perturbation we are supplying. So, if you supply a large input, you will get a large current output. Compared to the noise, this may be significant. So, the so called signal to noise ratio will be better or higher. If you give a small amplitude perturbation, signal to noise ratio will be poor, but you can claim that I can approximate the response as a linear system without any problem. If you go to large perturbation, the response will be good, but you may have non-linear effect. That means you may have 2 omega and 3 omega contributions, higher and higher contributions. Now, you can take any function and function in the time domain and convert it to frequency domain. So, any periodic function we can write it as a sum of sine and cosine. Here I have shown it as sine with a phase, that is the same as sine and cosine, and you can write the I as a function of time. You can write it in terms of constants and other coefficients, and the coefficients you can calculate using integrals. You can find it in any of the standard books, or you can search in the net, you will find those. I am not going to describe them here, but I want you to note the point that the blue line here is a continuous function. The red color circles represent equal time interval data, it is a discrete function. So, when you take data, when the current is measured, current may be converted to potential, it is measured, it is recorded in the system only at specific intervals, it is recorded at this points, it is not recorded in between. So, in between if the data jumps ups and down, we do not know that. And when you do Fourier transform of this discrete data, you can employ algorithms which are meant for discrete data. If you have a function, if I want to specify a function in an interval, in theory I actually have to give you infinite number of points. I can't just tell you this function has this value. When I specify this, I do not tell you anything about what is the value of the function in between. And if I want to specify it all the time intervals, basically I have to give from 0 to 1 second, but infinite number of data points. We have finite number of data points that we are going to handle, and for that we use discrete Fourier transform. And discrete Fourier transform, one of the algorithm is called fast Fourier transform, FFT. The advantage of Fourier transform is that you can obtain all the harmonics simultaneously. In one transformation you will get all the harmonics. All the harmonics means all the harmonics that can be taken from the data. If you have infinite number of points, you will get infinite amount of harmonics. If you have finite set of data, you will get only finite set of harmonics. The system may actually have more harmonics, but you will not be able to extract it from the data. The analysis is fast, and I want to show you some examples. Not the formula you can get it from books, you can get the libraries for MATLAB or any other program, most of them will have inbuilt libraries. But when you actually perform on a set of data, what would you see? Okay. Here I have constructed a sine wave, this is done in MATLAB. 50 millivolts is the amplitude, so you can see it goes from 0 to 50 plus or minus 50, and I have given a phase of pi by 4 radians, okay, 45 degree. So, instead of starting at 0 time, it is starting 0 will actually occur here, at 0 time it has a phase, and corresponding to 45 degree you are getting actually 90 degree and so on. And I have constructed 2 loops and I have given 16 points per cycle. You will get a finite number of points per cycle in actual data acquisition, and we use a function called FFT in MATLAB, but it is wrapped around another function called positive FFT. In theory, your data goes from minus infinity to plus infinity, or the sine wave goes from minus infinity to plus infinity. Frequencies also, any of the programming language by default will give you from minus infinity to plus infinity, but they are folded in a function called positive FFT. Just a wrapper library around the FFT program gives you frequencies only from 0 to whatever positive number you get. And the way it works, I have a sine wave, I will not give it until the end of the sine wave here, I will give it with 1 point less, because the way it works is it is going to take this and it is going to replicate this n number of times. Let us pretend and say this is the first point, second point, third point, fourth, fifth. So, what it is going to do is it will come here, next time interval it will step and then take the first point and put it, next time interval it will take and put this point, and so it will continue. Instead of this, if I give you points until this, means first point is 0 origin and so on, and the last point is here, it is going to shift to the next time interval and take this as the point and then reconstruct it, and that is not a sine wave, it is a distorted sine wave. So, if I want to give 3 cycles, I will give 1 cycle, 2 cycle, third cycle I will stop just before the end point. So, I will give data for n number of cycles, I can give 1 cycle full, second cycle whatever n number of cycles, but the last point I will cut it before I feed it to this. Otherwise, you will be scratching your head why it is not coming the way you expect it to. This is the implementation in MATLAB. Of course, if you write your own program or if you take libraries, you have to be aware of what are the constraints, what is the way to give the input and take the output. And because of the way that works, because it cuts off the frequencies from minus infinity to plus infinity, we are wrapping it and getting from 0 to plus, whatever value of amplitude you get, you have to multiply by 2. So, this is the command we have used here. E is the vector, we do not give time vector, we just say this is the sampling frequency. So, if the time is going from 0 to some value, we have 10 number of points, you have so many intervals, del t interval from one point to another, what is the time interval? Take that and take an inverse of that, that tells you what is the sampling frequency. So, you need to give sampling frequency, you need to give the vector, it will give you the frequency range and it will also give you the Fourier transform result. This is the implementation. How is it done inside the MATLAB? I do not know and I am not going through that. You can use an FFT program and get this. When you get the value, multiply by 2 in this implementation to get the amplitude. You have to add a phase of pi by 2 because your exponential value is cosine omega t plus j sin omega t. This is done as a complex transform. The y value you get here, the y vector in the frequency domain, it is a complex number. It is actually a complex vector. Absolute value tells you the magnitude and the phase can be obtained by using the command angle in MATLAB. You get the phase because we are giving a sinusoidal wave, we are not giving a e power j omega t, we are giving only a sinusoidal wave, you have to account for the phase offset. So, whatever value you get in the phase, add pi by 2 and for presentation I am multiplying by 180 by pi so that it gets converted to degree, otherwise you will just plot it in the radians. Because what has happened is in the FFT, it has split the energies or whatever amplitude you are getting and give it in minus and plus frequencies. It has distributed it equally. That is the way the FFT algorithm has been implemented in MATLAB. Now, we are throwing away all the negative one, half the energy is gone there, only the remaining half energy is here. So, we have to multiply by 2 to get this. Now, the first point in this vector, let us say you get a vector like this, what you get in the y frequency domain is going to be some number a, b plus jc, d plus je, etc. First number is with 0 phase, it is given some phase here, but it is the DC. So, when you write in Fourier series, first you write a0 and then you write a1 sin omega t, a2 sin 2 omega t with phase. So, a1 is without any phase, there is no sine or cosine there. In this case, because we are giving a pure sine wave, we do not expect to see any constant value. All that we need to get out of that is to say it is a sin omega t with a phase of pi by 4, that is all we need to get. Pi by 4 is 45 degree. So, notice the following, first point is the DC and that is 0, magnitude is 0. Second point, it is not showing anything, third point it is at 1 hertz, this is 0 magnitude, this is half hertz, this is 1, 1.5, 2 and so on. So, what it says is the magnitude is 50 millivolts at 1 hertz and everywhere else it is 0, and that is what we expect, we are giving a pure sine wave. It does not go up to infinity, it goes up to number 7. We can see only up to 7 hertz, beyond that we do not know what it contains. Okay. Phase value at this 1 hertz is 45 degree, that is correct, pi by 4 radians. Phase value everywhere else is meaningless, because if you take a vector and say its magnitude is 0, phase does not have a meaning. Phase has meaning only when magnitude is not 0. It does not mean the MATLAB will give you a 0 phase in those things, it just means that you should learn to ignore those. Everywhere else phase is meaningless. When you have non-zero component, you should look at the phase and see whether it is coming correctly. So, up to 7 harmonics are present, we have 16 point per cycle, there is a criteria called sampling criteria. If you want to see 8 hertz data, you should sample at least at 16 hertz. So, you should have twice the frequency that you want to sample minimum, and typically you want more because there is going to be noise in the system. If you give sine only, you will not get the correct phase, it is off by 90 degree. Okay. If you give the complex number cosine plus sine in the complex format for this, then it will give you the correct result. Just like the frequency is split into negative and positive, this also expects a complex input for this. We are giving only sine here, right. So, I would get the effective phase if I add pi by 2 here, because I am not giving it the complex feed. It is more of the implementation issue in the MATLAB, it is more of the way it is implemented for a general purpose. We are writing a program to wrap it and just cutting it to the positive frequencies. If you have image processing, you will have 2D data, you can do FFT on that, you can have 3D data, do FFT on that, but you have to be aware of how to use that library. I do not know if that is satisfactory. Okay, now what I have done here is to increase the number of points, sampling frequency is higher. Now I have 32 points per cycle, you can see it is more crowded here. and if I do FFT now, still first point is DC, second point is half hertz, 1 hertz is 50 millivolts, phase values are random for everything else, but at 1 hertz it is still 45 degree. Is it 45 degree? I had to check it, it does not seem to be correct here, I will check it and come back, but it will show you 45 degree if you do it correctly. Now the thing is, it is present up to 15 hertz. So if I want more harmonics, I should sample at a higher frequency. Sample frequency tells us how frequently we take data, okay. And if I take data at 100 hertz, the best I can get out of this is 50 hertz. I can't get a sine wave of, let us say, 100 hertz by sampling at 100 hertz frequency, because in one cycle I will sample only 1 point. The minimum I require is 2, typically I will need is more, okay. So here of course it is a perfect sine wave, so I show you data up to this and it comes to be, but in reality if I have other waves and it is distorted, if there is noise, I will not get good accuracy in high frequency regime, because I am close to the Nyquist criteria in terms of sampling frequency. Here it is not going to be much of a problem, because it is a pure sine wave. Now what I have done is sampled only up to 1 cycle. I have gone back to 16 hertz of sampling, 16 points per cycle. I have shown it in the same scale and then show it here that I have truncated up to this. When I feed it to the program, I will feed up to this level and then do FFT. 16 mean I should expect up to 7 hertz. I get up to 7 hertz. Also notice the interval is 1 hertz now. So if I want to get data at fine intervals, I want to know the amplitude and phase at fine intervals of 0.1, 0.2, 0.3, 0.4 hertz, then I need more time. I need to go for more cycles here. So the summary is, the frequency range 0 to what, 7 or 8 here, 0 to 15 or 16 depends on number of points per cycle, it is the sampling frequency. The resolution 0, 1 hertz, 2 hertz, that is one way of moving, 0.5, 1, 1.52, that is another way of going, 0.1, 0.2, 0.3, that is another way of going. The resolution I can get in the frequency, that depends on total duration. Another way to look at it is number of cycles. So here 1 is because of the time I have taken here. You can take f, 2f, 3f, 4f, and if you want less than f, 0.1, 0.2, 0.3 and so on, it needs to be done for longer time. Now in all these arguments, we have assumed that the frequency or sampling interval is identical. We are taking data at 0, 0.1, 0.2, 0.3, so many seconds or milliseconds. It is also possible that you can have data at non-uniform time interval, and there is a method of doing Fourier transform for that. We are not going to get there at all. We are going to say our sampling intervals are uniform, and we are going to look at data only with that assumption. Now when you actually take data, you send a command, software sends a command, usually goes to a board, data acquisition board, collects data. You would say take data at this interval for so much time, and there is a clock within the chip or board which is used to collect at those intervals. It senses all the time, but it will save data at particular interval. That is stored in a buffer and then transferred to the main CPU or to the hard drive. It does not send command 10 millisecond later send another command from the operating system. It sends a command to the chip saying acquire data for this much time at this interval, and the chip has a buffer. You cannot ask it to hold infinite number of data points. That is, you can't say give me high frequency sampling for long time. Each chip comes with a buffer. So there are limitations depending on which one is used in this. You can say sample every second for 100 seconds. It is possible it will do it. You cannot say sample every 100 seconds for 1 year. The chip size may be sufficient, but the chip also has a limitation on what is the maximum sampling frequency it can handle, what is the minimum sampling frequency it can handle, and you can't exceed that. Synchronization will not happen by sending it from operating system to that. So time interval is done at the chip level. So you can't tell I want many harmonics and I want fine resolution. Up to some level you can do that within the limitation. It is not that you have lot of storage and I do not mind waiting for a long time, but every minute take data and tell me that for. You can do that, but you lose accuracy if its command is going from the operating system. The time accuracy will not be good. if it is done at the chip level, time accuracy is better. But in general, because of this, there are limitations on how it is done in the actual chip level. There are limitations how data is acquired and given to us at the instrumentation level. There are other filters, digital filters that can be used to process the data. So, an example is freq command in MATLAB. If you look at the Fourier transform earlier, you get data at finite time intervals, you will get data at f, 2f, 3f, you can get data at half f, 1f, 1.5f, 2f. If I go for long time, you can also imagine I get 0.1 hertz, 0.2 hertz, but the frequencies are also at the even intervals. But let us say I do not want all this, I want only data at few frequencies. I want to look at data at 1, 2, 5. Of course, you can take the vector and do this, but you can use what is called filters, digital filters, and achieve the same objective. Again, you need to feed n-1 points for this implementation, and the way it called is it can be used to generate many other types of filters. This is a general purpose command. This is the vector of data 1, and they give the frequency range. I can specify here that it is going to be 0, 1, 2, 3, 4, 5, 6, 7 hertz or 0, 1 to 5 hertz, whatever I want here. Sampling frequency has to be given, and because of the way it is implemented, you also have to divide by the length of the vector to get the correct value, equivalent of FFT, and you need to multiply by 2 to get the magnitude, add phase offset of pi by 2, and you can do that and compare with the results in FFT. Here I have taken 1, 2, 3, 4, 5, 6, 7, 8 just like what we would get in FFT. Now, when you look at this, the red square fill square is the freq result, and FFT is given by the open circle, and they are the same for the 1 hertz where we have significant amount of information. At all other locations, this is magnitude is 0, phase value may or may not match, it does not matter. Whenever the magnitude is not 0, this command works correctly, it is fine. I can also say I do not want it everywhere, I want it only at 0, 1, 3, 5, and of course at 1 it will match, remaining it may or may not match, it does not matter. However, with this data, I can ask this filter to give me data at 1.5, 2.5, any number I want. Here I got only 16 points per cycle and I got 1 cycle. So, I can go up to 7 hertz, I can go at a frequency step of 1 hertz, I can go to 2 cycles, I can go at a frequency step of half hertz. If I say give me data at 0, 1, 2.5 and 5, it gives data at 0, 1, 2.5 and 5, no problem. I can also tell the filter give me data at 0, 1, 2.2 and 5. It will do the mathematical calculation and give me, except that it will give me incorrect information. Unless you are aware of it, you will process it further and get results, but they will not be correct. When they implement it in the hardware also, they will have to use some tricks. Single sign is usually not a problem, multi sign you will have problems. Okay. I want you to go through the details and see, but right now I want to emphasize that if you ask it to give data at a higher resolution than is possible theoretically, here I want data at 0.2 resolution. It gives data at 0, half, 1, 1.5, 2, 2.2, that resolution is not possible, I can get only at 0.5 resolution. If I want data at 0.2 resolution, I need more number of cycles. If you do Fourier transform by FFT and get the array, you will see you do not have 2.2 there. If you do this filter, it will give you an answer, but you will get a wrong answer, you will not get any flag or indication saying you have a problem.
So, for the send you like you specify the resolution by just setting points, right?
You do not specify resolution, you tell these are the frequencies at which I want the power, magnitude and the phase.
So, it will decide the resolution based on the decimal?
It does not decide the resolution, it applies the algorithm whatever it has inside. I do not know the algorithm there. Internally it uses FFT at some level, but basically you have digital filter. When you are using it, you have to be careful whether you are using it in the software or whether it is implemented in the hardware. You have to be careful in the sense when you ask, that time you have to verify whether your request is correct or not for the given set of data, for the given time interval and given total time, whether the request is correct or not. If it is not correct, you will not get the correct result.
So, this 0.2 problem is because the resolution of the algorithm itself does not go below 0.5?
No. If you give data up to 10 cycles, it will go in 0.1 interval, no problem at all. It is not the algorithm has a problem. My feed and request to the algorithm, that combination is not correct. If you give correct feed and the correct request, it will give me the correct data. If you give this feed, I should not ask anything better than 0.5. I can ask at 0.5, I can ask at 1 hertz, no problem. I can't ask 0.7. If I want 0.1, I should give that many number of cycles. If I want 0.1 resolution, I should give 10 seconds. If I want 0.01 resolution, I should give 100 seconds of data. Then it will give me the correct result. Problem is, if I give a wrong request, I will get the wrong data and probably I will proceed with the analysis without knowing that there is a problem. That is more dangerous. If you do not get it, it is okay. You have a problem, but you know that you have a problem. Danger is when you get data which is not correct and you assume or you believe it is correct. It is true in experiments also. The equipment gives you a problem and you do not get data, it is not pleasant, but you know there is a problem and you will try to fix it. If it gives you garbage data and you do not realize it is garbage data, it is really a problem, because you will come to conclusions which are not correct. Similar to FFT, there is another technique called cross correlation. Let us say you have a sine wave or you have a signal which can be written in Fourier series like this. You can write sine A plus B as a combination of sine and cosine. Same way you can write this sine omega t plus phi as sine omega t cosine plus cosine omega t sine phi, which means when I write it in terms of omega t alone, I can combine this and say for a given phi this is a constant. So, I can expand this as sin omega t plus cosine omega t, sin 2 omega t plus cosine 2 omega t. This is another representation of Fourier series. Fourier series can be sin omega t plus phi. It can also be sin omega t plus cosine omega t with different coefficients in front of them. Now, these sine functions are known as orthogonal functions, meaning if I take a period t, I will get 0. Sin m omega t and n omega t, as long as m is not equal to n, I will get 0. If m equal to n, I will get a value, I can normalize it and get the factor out of this. Likewise, you can use this for cosine also. Sine and cosine functions are orthogonal, which means if I take the function I, which can be expanded like this, and then I do the integral, I will get the component only corresponding to the sine. Everything else will go to 0. Same way I can do it for cosine. So, I can get the coefficient of 1s and 1c by doing this integration. I can get the coefficient of 2s and 2c by multiplying by sin 2 omega t and cosine 2 omega t and performing the integral. This method is called correlation, cross correlation. I can get the phase by doing the sine and cosine. I can get I1s and I1c, which means I can back calculate and get phi 1. This method is slower compared to the FFT analysis, and for each harmonic you have to do the calculation. FFT, once you do the calculation, you will get 0 to 7, 0 to 15, whatever I have shown in the example, you will get it. It is not that you will get only the first harmonic and you have to do extra effort to get the second harmonic. You go through the effort, you get the entire vector out of it. Here you have to do it multiple number of times, and these are usually done at the chip level. It is not that data is taken and then processed in the software. Then you can even try parallel processing. These are done at chip level, and usually you get only one harmonic, fundamental harmonic out of the lock-in amplifier. Although you can set it for other harmonics, but if I want to acquire data with the normal lock-in amplifier, I will have to run it once at the fundamental mode, run it again at the second harmonic, run it again for the third harmonic, and so on. So, it is going to be slower. System might have changed between the runs. That is a possibility. Anyway, runtime becomes much longer than what you would get in FFT, but this also happens to be more accurate in terms of ability to reject noise. So, implementation is slower, multiple harmonics need multiple calculation, it has a better signal to noise ratio when you compare to FFT. So, whatever we have seen so far is for a single sine. What happens when I add two sine waves? This example, I have shown you 1 hertz and 2 hertz. I have shown them as continuous lines, it is of course generated using discrete points. You can see the combined wave, they have 0 phase, they have equal amplitude of 2, whatever that value is, it is not specified whether it is volts or millivolts or anything. Total is not going to go until 4, because these are at different frequencies, and you will get a combined wave. This has a period of 1 second, this has a period of half second, combined wave has a period of 1 second. That means, if I give you this data, you can replicate it n number of times, you will get the wave that we generate from this. And when we do Fourier transform, you get 1 hertz, I got 2 as a magnitude, 2 hertz also it is a 2 as a magnitude, 1 and 2 hertz the phase is 0, it is what we would expect to see, no problem. Now, if I apply this to a circuit, I will get current. I can do the FFT on the current. I will get similar to this, I will get 2 other graphs saying this is the magnitude of current, this is the magnitude of current, this is the phase value, this is the phase value. So, I can get the ratio of magnitude, I can subtract the phase, I can tell this is the impedance, based on these 2 values, I can tell the magnitude and the phase of the impedance at the same 1 second data acquisition time. Normally, I will have to do 1 second here and a half second here, 1.5 second, that is the absolute minimum. We will forget the data processing time. But if I combine these waves and send this as one wave, as long as I can do the Fourier transform, I can get the impedance at 2 frequencies in a shorter time compared to doing it separately. If I send it at 1 hertz, 2 hertz, 3 hertz, 4 hertz, I will have to add those times and say this is the data acquisition time. Now, I can combine all those waves, send one, get the output, do Fourier transform of the input as well as the output. Fourier transform of the input, we should know what it is, but we will anyway do this process and then compare and get the results. You can get the results of impedance as a function of frequency. Okay. But there are pitfalls, we will continue with this tomorrow.